And to clearly explain what machine code and assembly language are, how they relate to processor architecture, and how programmers and hardware designers use binary instruction encoding to perform operations like additions, subtraction, and memory access. Now, this will be done in a way that is engaging, hands-on, and suitable for learning. Now, let's begin with the fundamental idea here. Computers can encode logic as data. Now, that might sound simple, but in reality, it's actually what makes modern computing so powerful. Early mechanical calculators could add and subtract numbers, but they couldn't change what they were doing unless you physically rewired them. Now, computers can store instructions in memory, just like they store the numbers, and then read and execute those instructions. And this is called the machine code. Now, it's the set of binary instructions that the processor understands natively. Now, example, you can write on this, for example, binary. Now 0, 1, 1, 1, 0, 0, 1, 0, and 0, 0. Yeah, this is just a bits, right? Now, with these zeros and ones, we are basically telling the CPU to add 2 to the value in R0 and store it in R1. So instead of being locked into one task, a computer can change behavior instantly. Now that's how we can install new software, update an application, or upgrade our operating system, and all by changing this code that the CPU runs. Now think about it. How does a CPU know what to do when it sees a stream of ones and zeros? Now this is where instruction encoding comes in. So every processor has something called the instruction set. Instruction set architecture, or ISA. So this is like a language manual for the CPU, defining how every combination of bits should be interpreted. Now, let's say we are designing our simple CPU. We will need to define what instruction exists. Like, in this case, we will add the add, subtract, and load. And we need to assign a unique binary pattern, like an opcode, to each instruction. And we need to decide how many bits to use and how to divide those bits among the parts of the instruction, which is what? Operation, then it will be, we will say inputs and outputs. So here what we will basically do is we will give an add here. What, let's say we want to give it, let's say, yeah, it could be a random number. It shouldn't, it is not obligated to use bytes or just signed characters here. So we can use 7 bits, 0, 0, 0, 1, 1, 1 0. So this is for add, and let's also use the sub, which is subtraction. 0 0 0 1 1 1 1. Now these binary patterns are called the machine instructions, and when you write a program in binary, that is what you are writing. And writing binary by hand is tedious and error prone. Now instead, programmers use something called the assembly language. This is a symbolic version of a machine code. So each instruction has a mnemonic. This is a short code word to represent it. For example, this is add for addition and sub for subtraction. So here's how our earlier this mnemonics will look in this case here. So we have the operation it does, let's say addition. The opcode it has in this case, it is 0001 1110, and it is the mnemonic is the add. And so we are basically creating a dictionary for a CPU here. So this is for us, right? The operation is for us. Operation it does for the this is for the programmer that will use this architecture that we are developing here. And yeah, so this is a opcode in bits, and here this is a mnemonic how we want to represent in assembly language. So we will also have the subtraction. So in our subtraction opcode, we will again 0 1 1 1 0, no 1 1 1 1, and this is what sub. Assembly code is human readable but maps directly to machine instructions. So assemblers convert this into binary the CPU can run. Now, think of a machine code as a music written in binary and assembly as the sheet music. So you play the same tune, but one is easier for humans to read. So we can say that assembly is basically the machine code. So you may also ask here, where do numbers come from? Oh, so yeah, we are using numbers to use registers. So when we add numbers, we have to specify what to add and where to put the result. So CPUs use register to store temporary data, and registers are small storage locations built directly into the CPU for fast access. And in this example, let's say let's write this code here. Add register register 1, register 0, 2. So register 0 is the source. This 2 here is an immediate value. Let's actually use different color. And the R1 here is a destination register. So this is where the result is stored. So registers are crucial because reading from memory is slow. So using registers keep things fast and efficient. And another thing you need to learn here is the instruction format. So we will put it all together here. So let's assume we are building a 16-bit instruction. That means every instruction is exactly 16 binary digits long. So we'll break the binary down. So, but first I will open a new blue board here. Okay, so what we will do here, we will arrange 7 bits for opcode. So the opcode is basically means what operation to do. You remember from this previous lecture. And we will save 3 bits for the immediate value. This is a constant number, let's say. And we will save also 3 bits for source register. So we will write this as Rn, and we will save 3 bits. We will just to speak more correct, we will use 3 bits for the destination register, and in code we will write this as RD, D for basically for the destination here. So what we will do here is in op we will have the 7 bits, 7 bit. This is basically the op, and in the constant number we'll have 3 bit. In the source register, which is Rn, we will have again 3 bit, and in the destination register we will have again 3 bits. So let's manually encode this instruction. So operation is add, to so let's break it down. So remember from the previous lecture, the add is 0 0 0 0 1 1 1 0. This 2 in binary is 0 1 0, and the R0, let's say hypothetically it is 0, and R1 is 0 0 1. So the full binary instruction is 0 0 1 1 1 0 0 1 0 0 0 0 and 0 0 1. And if we convert that into hexadecimal, it is going to be 18C1 X, yeah. So this is basically how it is in hexadecimal. Now let's do another example. Let's say sub. By the way, you can change this places with each other, so it doesn't matter the arrangement of this here. Basically we are creating a new architecture hypothetically. So yeah, again, let's say 2 R1 or R0, or yeah, let's do the same, R1. So here, remember from the previous lecture, the sub we assigned it 0001. So in this case, 0001, 1 and 4 ones here. Yeah, 1 1 1. And now it is time to this. Yeah, there's gonna be again sign 000, and again here it's gonna be 001. And this is the thing for the second instruction. So that's how it basically works. Now, of course, writing binary manually like this is impractical. So most assemblers can convert from this readable format into a final machine code. So you can write a simple program that does not does this conversion automatically from this assembly languages to machine code. So you don't need to worry about bits and bytes here. Mostly, not the mostly, but I can say like 20% of the times, and you will see why I'm saying that. So let's also add the LDR instruction. You remember load instruction. So we need to access the memory as well, right? So what we'll basically do is, so yeah, so far we have covered the arithmetic instructions like the add and sub, which operate on the data that's already inside the CPU's register. But what happens when we need to use a value that's stored in a memory instead of in a register? Now this is where new kind of instruction comes into play, which is the load instruction in our so-called our own instruction set architecture by Typhoon. Yeah. Now let's assign the opcode for this instruction. So also write this here. And why we are using so much reds here? I don't like the reds. Yeah. So we will use the load. So for the load instruction, opcode is going to be, again, let's use the 7 bits. So 1 and 000. So mnemonic is going to be load So what we will basically do here is we have also give the opcode operation name and the mnemonic for this. Operation name is just for us to see what this instruction does. So we will say our load instruction takes 2 operands. It takes 2 operands, a register that will receive the data, so destination, and the register that contains the memory address to load from memory, right? So it's called the source reg. So now let's define our registers just like before. So we have a register, let's say R0. Let's actually use the different color. So we have a register R0 is 000, R1 is 001, R2 is 0 1 0, and r, oops, yeah, r2 0 1 0, and r3 is 0 1 1. Now that's good. So if you want to write the load r3 r2, that means the load the value from the memory address stored in R2 and put it into R3. So let's encode this instruction. You won't need this in real life to turn this instruction to machine bits and bytes, but this is, will be very helpful for you in your learning process. Yeah, now let's get the opcode. You remember opcode was 3 zeros, 1 on, and 3 zeros again from here, oops, from here, and again. So here we have 0 1 0 on the R2, 0 1 0. So, and we also have 0 1 1 for the R3, and 3 bits is unused, reserved for feature, so we will say just 0 0 0. So this is, let's say, reserved. Remember in our previous, yeah, it is deleted here, yeah. In our subtraction addition we will use this 3 bits, but in our load we don't need that 3 bits, so we will just write it 0, saying that it is reserved for now. Also, this is not a good practice to use reversed bytes in the registers, but you see we have instructions for these places. CPU will not see this as anything, but yeah, it's good to keep a mind on this bits. They should be unique for each instruction here, so you can't use these bits and this one and this bits on this one, right? Yeah, and you will learn that nitty-gritties of assembly language as you advanced more in these lectures. So yeah, so the final 16-bit instruction basically becomes this. So you can write as a binary and hex version on your own to reinforce it, and yeah. So we also have another question you may ask here. What happened during the load? Basically, first it reads the value in register R2, which is in R2 it is 0 1 0 0. Now it treats that value as a memory address, and it goes to the memory location. It reads the value stored at, for example, here, and it stores the value into the register R3. And this is called the indirect addressing. So we are using the contents of a register to point to a memory location. So basically R2 goes to 0 1 0. So basically says the memory, hypothetically speaking, like it here it doesn't say anything 42, but so R2 goes to here and says the memory has value 42, so, and it is load to R3. And we can also write the opposite of the load, which is what? The store. So We often also want to write values from a register back into a memory. Now this is done using this store instruction. Just I'm saying that hypothetically. So this is just we are creating our own instruction set architecture now. So to be prepared for the next lectures. And yeah, now this will store the value in R3 into the memory address pointed to R2. And of course it will have a different opcode. Let's say for the opcode it will have 0001001 and as a store and storage. And yeah, so you may ask, what is the equivalent of the load in the real ARM architecture, instruction set architecture? It is the LDR, which you will learn in the next lectures. Now let's review what we have learned today in this almost half an hour lecture. So machine code is a binary language that the CPU runs. Assembly is a readable version using mnemonics like add, sub, load, and there's so much mnemonics here. And every instruction is encoded as a series of bytes that follow specific rules. And remember, registers are fast local storage units that keep temporary values, and memory access using indirect addressing via instruction like LDR. And in our own architecture set we use this load. And yeah, in a real CPU like ARM, there are hundreds of instructions, but understanding a small subset like the add, sub, and LDR gives you a solid foundation. Now, I'm Typhoon. Thank you for watching, and I'm waiting you in next lecture.